This video is going to help you with the build your own capacitor lab. So here's the symbol for capacitor, and it kind of gives you a hint in terms of what you're going to do. What you're going to be doing is putting some aluminum foil down to represent one of the plates. You'll be putting some material in between to allow some separation between the plates. Then you put another piece of aluminum foil on top. You'll attach the bottom piece to one side of a capacitance meter and the upper piece of aluminum foil to the other side of a capacitance meter. The capacitance meter measures the capacitance. So how is it affected by several things? One is the plates and their area. Another thing is the separation between the plates. And the final thing is the material that you put in between the plates. The stuff that you put in the middle here. And we're going to try a few different things. So you're actually going to be experimenting with that in lab when you do it. So I want to give you a little bit of the theory behind that, behind how these values contribute to the value of the capacitance of the parallel plate capacitor. So remember, this is an equation I talked about in class, that this describes the relationship between the charge on the plates of the capacitor the voltage across the plates of the capacitor and the value of the capacitance of the capacitor itself. Okay, so this is a really useful equation for us. You could rewrite it as C is equal to Q divided by V. Okay, new slide. So here's where we're going to use what we learned in the last lecture or two of class. If you remember, if you have an infinite plane here, which we're going to take one of these plates to be, and you have another infinite plane here, and this infinite plane has positive charge on it with some charge density, and this infinite plane has negative charge on it with the same charge density, because other than the fact that one is positive, one is negative, the charges on these two plates are identical. We came up with a value of the strength of the electric field in between the plates. The direction, of course, is from the positive plate to the negative plate. We talked about the fact that the strength of the electric field is uniform between these plates. It's the same everywhere. Okay, so it's the same everywhere in between the plates, and it's going to be equal to the charge density on the plates if there were just one plate divided by epsilon 0. But since there's two plates, so in between, if there were just one plate, there would have been a 2 here in the denominator. Whoops. There would have been a 2 here in the denominator, but since there are actually two plates, there's also a 2 up here, and those two twos cancel. So the electric field between the plates is simply the charge density divided by epsilon 0. So if I go to the next slide, again I'm going to remind you what the electric field strength is between the plates, and it's uniform everywhere in between there. It's sigma divided by epsilon 0, simply because there are two plates, so their effects add, and this is the result we get. And so sigma, of course, is the charge divided by the area. So the electric field then becomes Q divided by A epsilon 0. That's the strength of the electric field between the plates. So what's the voltage, or the potential difference between the plates? If we have two plates here, and they have a uniform electric field between them, with this value here in it, the potential is equal to the integral of E, the electric field, dot dx, where x is this distance here, and dx is the incremental amount here. So that's dx. Small amounts all the way that you integrate up to get this full distance x here. But what's nice is if the electric field is constant, then it's just, you pull that out of the integration, and v just becomes the integral of dx times e, which is e times x. it's the same thing as if when you're integrating the equation for work is equal to the integral of f dx. If f is constant, you're just simply multiplying f times x to get the work done. Okay, so this is the potential difference between the plates, E times x. And x here, I'm going to call that d, where d is the spacing between the plates. So I'll call that d. Go to a new slide. So, just to remind you where we're at, v is equal to E times d. E is equal to Q divided by A epsilon 0. So that means that V is equal to Q d divided by A epsilon 0. That's the voltage between the two plates, or the potential difference between the plates is this expression here. So now let's calculate the capacitance. Going from Q equals CV, the capacitance is equal to Q divided by V. So I take Q, divide it by V, which is this here, and I have Q d divided by A epsilon 0. That tells me that my capacitance is equal to my area of the plates times epsilon 0 divided by d. Just take a look at this conceptually. If I increase the area of my plate here, increasing the area means I can store more charge for a given voltage. So conceptually that makes sense. If I increase the spacing between my plates, or if I decrease it, if the plates get closer and closer together, that means, if I have a plate here, let's say, and I have a plate here, one is positively charged, one is negatively charged. If they're closer together, I'm going to be able to get a lot more charge on this plate because it has these other negative charges so much closer. So it's going to attract more negative charges to the blue plate and more positive charges to the red plate than if they're further apart. That would mean a greater capacitance. So capacitance is a function of the geometry of the situation here. Notice it's not a function of the charge, it's not a function of the voltage directly. It's actually a function of the area of the plates and the separation between the plates. Okay, so there's one other thing I want to tell you, is that the capacitance can also be affected by what you put in between the plates, and I hinted at that at the beginning. Whatever material is in here, if you have some material in there and you have some positive charges on one side of the plate and some negative charges on the other, this material is an insulator, but inside the insulator you have little molecules, and the molecules, the plus side of the molecules is going to want to face the minus side of the charges. So you're going to have this going on inside the dielectric material here. This is going to allow even more negative charges and positive charges to accumulate on each of these plates. So by putting the right material in between these plates, you're actually going to increase the capacitance of your capacitor, your parallel plate capacitor. So the full equation for the parallel plate capacitor looks like this. A times epsilon 0 divided by d times another quantity which I'm going to call kappa, which is called the dielectric constant. Of the material that you're putting in between the plates. So in lab, you're going to explore different types of dielectric constants. You look at cardboard, you look at paper, you look at saran wrap. You could try almost anything that's an insulator and put it in between these plates and see how it affects the capacitance of your capacitor. Okay, good luck in lab. If we look at that equation for the electric field, between the two plates, the charge density, of course, is equal to the charge divided by the area of the plates. Okay? So that tells me that the electric field is equal to 2q over A epsilon 0.